Okay, so when we talk about the empirical rule, we're talking about the normal curve. So let's see if I can draw this semi-normal. That's not too bad. So remember the normal curve is when we have our distribution that is symmetric. So both sides are the same. We could fold it down the middle and it would match. And it's got that bell shape. So anytime we're dealing with data that is distributed in this way, we can use these rules. So remember, this is the mean. So let's say that the mean of my sample is 70. Okay, and let's say that the standard deviation of my sample, will make it something easy to calculate, is 5. So if the mean is 70, this would actually come down like this, tail off. We're usually looking at 3 standard deviations above and 3 standard deviations below the mean. So every time we go a standard deviation above, we add that value one more time. So it'd be 70, 75, 80, 85. And as we go below the mean, we just subtract it. So 65, 60, 55. Now the empirical rule typically goes 68, 95, 99.7. And different books or different resources might give you a slightly different number, especially on that last decimal, but that's about where it is. So what this says is, within one standard deviation of the mean, there's 68% of the data. So 68% of all of my values would fall within 65 and between 65 and 75. If I said, what percent of the outcomes fall in the range 65 to 75, I would say 68%. If I said what percent of the test grades were between 60 and 80, well, that's the next step. That's 2 standard deviations on either side. So within 2 standard deviations, we have 95% of our data. So anything in this whole region, that covers 95%. So within 1 standard deviation is 68%. Within 2 standard deviations is 95%. And then within 3 standard deviations, that's where we get that 99.7. Now notice that that's not the whole graph. We've got these 2 little tails out here. And if we look at that, then we've only got 0.3% of the data that we haven't accounted for. So if we split it in half, remember it's symmetric, this little tail is 0.15%, and this little tail is 0.15%. Now it's symmetric, so we can split this up into smaller pieces. So if I just wanted to know between 65 and 70, this is 34%, and this is 34%. So let's see, 95. Let's do a quick breakdown of each one of these sections. Make sure I don't tell a lie. So if this whole portion here is 95%, well, 68% of it's here. That means I've got 27% left over. So if I split that in half, this little sliver between 60 and 65 is 13.5. And this little sliver is 13.5. And then 99.7 minus 95 gives me 4.7% that I have left in these two little pieces. So if we divide that by 2, since it's symmetric, this will be 2.35%, and this would be 2.35%. Now, if I asked how many people scored better than 70, 70 is the mean, and it's right there in the middle. So better than 70 would be 50%. That's half of the data. Below 70 would be half of the data. If I said how many or what percentage of the people scored above a 75, we could add each one of these pieces together and find out what that value is. Okay, so that's the empirical rule and the normal curve broken down a little bit. What other questions? Let's see. What other questions do we have as far as the stuff from the last couple sections go? I think this applies to numbers 6, 7, and 8 on that stat crunch where it's talking about the histogram. So I would sketch this out separately. Make sure you label the mean and all of the standard deviations. Break it down into those little pieces so that you know how much of your data falls within each one of those little sections of your graph, and then add it together or give the ranges as you need to. Okay, what else do we need? Good question. Okay, I don't see any other ones, just giving you guys a chance to type. I know sometimes it's harder to type in questions than it is just to ask in class. So if there's anything else that comes up, just type it in. For now, we'll switch over to some new stuff. Okay, so I'm going to make it so I can see your chat box. So if you have questions as I go, I can see them. And you can stop me. Also, feel free to unmute and ask. All right, so chapter 4, we're going to go ahead and get started on this one. And we're talking about describing the relationship between two variables. So we've been talking about one variable. We can find the mean for one, the standard deviation for one. But what if we have two variables at the same time? And we kind of started talking about this at the very beginning when we talked about like response variables and stuff like that. So we're going to continue on with that idea today. So this will be posted again. I'll post the video from class and the notes. So if you need to go back and look, it'll be there. Okay, so response and explanatory or predictor variables. This is probably something that you've looked at in a science class. So anytime you do an experiment and you're trying to compare what's happened, we've got the response variable that we're trying to measure. And that variable can be explained by the explanatory or the predictor variable. So when we look at a scatter chart, a scatter graph, a scatter diagram, whatever your book or your resources call it, it's going to show us the relationship between those two variables. Now we're only talking about quantitative variables. This doesn't apply for qualitative. Remember, we're a little bit limited in the way we can represent a qualitative variable. So we're going to shift over into mostly quantities at this point so we can do lots of calculations. So each individual in the data set is going to be represented by a point in our scatter plot. And remember, the explanatory variable is always on the horizontal axis. So usually we think about like time being on the horizontal axis, something that we haven't manipulated. This is our guideline. So maybe I took a measurement every 5 days or once a year or each quarter. That's not the only case where we have an explanatory variable, and we'll look at some examples, but that one's really common. And then the response goes on the y-axis, and that's what we're measuring. That's what we're trying to see a pattern in. Okay. So hopefully you have your calculator nearby, and we're going to work through this one together and make sure that you can find all of this data. So in your calculator, go to Menu and 2, and let's enter this data in those 2 columns. So looking at the data that we have here, we're looking at the depth where we begin drilling. So you guys type that in, and then we'll continue from there. Okay, so we're looking at how long it takes us to drill. So if you have that entered, I've got it in my calculator. And we're gonna look at what our calculator will do with this. So let me switch over. And I've got mine typed in. Oops, I hit a button. There we go. Okay, so this is what your calculator should look like. You got your data listed into your list 1 and your list 2, just the way it was in that chart. And if we want to look at the graph of this, we just have to press graph. So if we press graph right there, it's going to show us, oh, and graph again, sorry. It's going to show us what that scatter plot looks like. So looking at that scatter plot, I think, well, this doesn't look like a super strong relationship, but I can see that there's kind of a pattern here. So if I had to draw a scatter plot, this is exactly what it would look like. Now, there's some more information that we need to find out here. What if we wanted to come up with, well, hold on, I'm getting a little bit ahead. Let's go back to our directions here. So it says draw a scatter plot, and we did that. And ours looks just like that. Your scale might be different. But it's the same information, and it looks pretty much the same as mine did when I typed it in the calculator. So we want to be able to describe the relationship between these 2 variables. So if we look at the relationship here, how could we describe it? Well, there are a couple of ways. If we're graphing an explanatory and a response variable, we could have all kinds of different patterns. So A and B are both linear patterns. So those 2 on top, those are straight lines. And we're going to talk about the directions of these lines, but notice on A, it's increasing. So if I drew a line through that graph, that slope would be going up. So that's a positive relationship. On B, if I were to draw a line through there, that's a negative relationship. The ones across the bottom are not linear at all. Now, it doesn't have to be a linear relationship, but those are the ones that we're going to focus on right now. So if we're going to focus on linear relationships, C is probably a quadratic, so like negative x squared. D might be cubic. And then E, that's kind of constant. We could draw a line straight across through there, but we would just say that there's no linear relationship. So we want to be able to describe what these relationships look like. Now, just like we've done so far, first we start with the description. It looks like it's linear. It looks like it's not linear. It looks like it's positive or negative. We did the same thing when we talked about things like outliers. Well, it looks like an outlier, but then we came up with a way to calculate a value so that we could say this is definitely an outlier. It falls outside of the boundaries. So looking at the difference, we don't have to read this whole long paragraph to find out what positively associated means. So as one increases, the other one increases. It's a positive relationship. On the other hand, we have a negative relationship. As one variable increases, the other one decreases. So we're going to talk about, we know that we can look at the scatter plot and say this is what it looks like, but we're going to talk about a value so that we can actually determine what this means. So this is called the linear correlation coefficient. And I know that this says that we use the Greek letter rho, but typically we just use an R because usually we're dealing with the sample correlation coefficient. That's the most common. And that's the one we're going to see in our calculator. So when we're talking about linear correlation coefficient, we're talking about that R value. And it's going to tell us how linear it is and what direction it's going in. Okay, so if we're going to calculate the sample linear correlation coefficient by hand, this is the formula. Remember, the big E means sum. So we're supposed to find the sum of, now remember we're dealing with two variables now, our response and our explanatory variable. So you've got an X and a Y. So the difference for each value and the mean over the standard deviation times the value minus the mean over the standard deviation for the other variable. We're supposed to add all of those together. So in that last problem, I think we had, hold on, let me double check how many. 12, we had 12 pieces of data. So you would have to find 12 products and add them all together and then divide by n minus 1, or it would be 12 minus 1, which would be 11. So we would have to find all of this information in order to calculate it by hand. Now this is where it comes from, but we don't have to do it this way. So we're going to calculate one here in a minute, but these are properties and these are super important. We have to know what it means if we're going to use it. So properties of our linear correlation coefficient. It's always between -1 and +1, always. It doesn't matter what your data is, when you find that linear correlation coefficient, it's always going to be between -1 and positive 1. If it's positive 1, that means that it is a perfect positive linear relationship. So it's a perfect straight line with a positive slope. That's what that means. If it's negative 1, then it's a perfect negative linear relationship. So it's a perfect straight line with a negative slope. And the closer the value is to positive 1 or negative 1, the stronger that linear relationship is. If it's far away from positive 1 or negative 1, so the closer it gets to 0, the weaker the relationship is. So it's this continuum between negative 1 and positive 1 where we start out perfect, and then the closer we get to 0, the less linear we get, and then the closer we get to positive 1, the more perfect we get. Again, I'll post this, so if you need to go back and look at it or make notes, you can. But if I go too fast, just stop me, type something in the box. So this is what we just said about being close to 0. Being close to 0 doesn't necessarily mean there's no relationship at all. It just means that it's not linear. Number 7 says that there's no units when we talk about correlation coefficient. And we have to be careful because correlation coefficient is not resistant. So remember, mean was not resistant. It was pulled in the direction of whatever those extreme values were. So if we had an outlier, the mean was really affected by it. If you had pretty good grades and then you skipped a test and never made it up and got a 0 on it, it would really pull your test average down. But a median wouldn't be as affected. It was more resistant. So correlation coefficient is kind of like mean. It's not resistant. So we have to be careful with those extreme values. And it's always a good idea to describe them, where they came from, or try to explain it. Okay, so let's look at some examples, and it helps when you see some actual graphs and what the correlation is. So when we're talking about correlation coefficient, notice A is a perfect positive linear relationship. And our R value, our correlation coefficient, is positive 1. Positive relationship, positive correlation coefficient equal to 1. Now looking at B, it's still strong and positive. If I were to graph this and not have a correlation coefficient, I would probably tell you that there was a linear relationship there and it was positive. Notice they have already calculated the correlation coefficient and it's 0.9. So that reinforces my observation that this was a strong positive relationship. If I were to use a line, if I put a line through the middle of those points and wanted to use it to make an estimation, it would be a pretty good estimation. There would be some variance, some variation in there, but it would be a good guess. Moving on across, if we look at C, that correlation coefficient is 0.4. Notice how much more spread out those points are. Our data doesn't follow as strong of a pattern. So it's moderate. I can still draw a line through that data and make a reasonable guess, but it wouldn't be as good of a guess as graph A. So graph A would be perfect. Graph B would be a good estimation if we used a linear correlation, which we'll talk about in just a minute. And C would just be okay. D is the opposite of A. So it's perfect, but it's negative. So that's what our negative correlation looks like. And E is kind of like B. It's strong and negative. Our linear correlation coefficient for this one is about negative 0.9. So notice it's negative. So the slope of the line that goes through that would be decreasing, would be a negative slope. But it's a strong relationship. So it's close to -1. F is kind of like C, but it's the negative version. And then when we get to G, there's not a linear relationship here. That correlation coefficient would be extremely close to 0. We couldn't make a good prediction for that graph. It's too scattered. There's not a good linear relationship. No correlation on that one. For H, there's a pattern. We can see that this is probably like a negative x squared kind of situation where we've got an upside down parabola. But it's not linear, and remember, that's the only thing that a linear correlation coefficient is going to tell us is if there's a linear relationship. So if there's any other kind of relationship, our linear correlation coefficient is not going to be helpful. Okay, so looking at this one, we're supposed to describe the linear correlation. So looking at this information, how would you describe the correlation coefficient? You can make an estimate or just describe the direction, but type it in the box. What do you think is going on here? Positive or negative, strong or weak. You could make an estimate between -1 and +1. Yeah, strong positive, that's a good explanation. That's a good description. It definitely looks linear. It's a positive relationship because it is increasing. Yeah, it increases from left to right. So that tells me I've got a positive slope or a positive relationship. Now, it's not a perfect line, but we can definitely tell it's a line. Notice in quadrant 1 how spread out that 3 by 3 section is close to the origin. That's going to make it less linear. So remember, anything that doesn't follow the pattern is going to have an effect. So we know it's positive, maybe like a positive 0.7, positive 0.8, somewhere in there for this one. We've got some scatter, but we know it has a linear relationship. Good job. So yeah, when we're looking at outliers for a linear graph are ones that don't follow the pattern at all. So that 3 by 3 block in quadrant 1 near the origin, that makes it less strong because they're more spread out, but it's not necessarily an outlier because it still follows the pattern. An outlier would be like a point out where the Roman numeral 2 is. So something that doesn't follow the line that we have. So it definitely increases how spread out it is, but not necessarily an outlier. That's a good question. That's just the variation of the data is how we would explain those points. Okay, so let's go back to the data that we were looking at earlier. Here's the same chart with the same information. Hopefully you've got that in your calculator still. They want us to determine the linear correlation coefficient of that drilling data that we had. Now, if we were doing this by hand, look at this table that they've created. So they didn't necessarily do it by hand. They used like Excel or something to help them. But notice each column is a portion of that equation, that formula that we were looking at earlier. And then once they get all that information all together, they finally get to a correlation coefficient of 0.77. So let's go back to, let's figure this out a little bit. Let's go back to our calculator. Mine's already timed out. So we've already looked at the graph of this. We decided that it was positive, arguably linear, moderate to strong linear correlation here. Let's go to calc. So you can get here from this screen or from where your data is. But if we go to calc, let's find the linear correlation coefficient. We're going to go to the X option. And then AX plus B. So we're just going to find the equation of the line that best fits this data. So when we get all this information, we've seen A and B before. Y equals AX plus B is like the basis of algebra 1, right? If you can find the equation of a straight line and do stuff with it, that's half of algebra 1 class. Sorry, there's a puppy chewing on my chair. So if you can hear that, that's what it is. A is our slope. B is our y-intercept. And that R, look at that R value, 0.77. Isn't that exactly what they found after they did all of that work to find the correlation coefficient? So based on what we know about correlation coefficients, that's a pretty strong, moderate to strong correlation coefficient with a positive relationship. Now we haven't gotten to R squared yet. We'll get there. So for right now, it's just the R value that we're talking about. The R squared is just simply the R value squared. They're just saving you a step there. So we can draw this in. And there's my scatter plot with my line of best fit in it. And speaking of algebra 1, you've probably done this before. Hopefully you have. Had a scatter plot and found the line of best fit. Basically what this class does is just takes it a step further. We want to find the line of best fit, understand how they got it, and be able to accurately describe it. And not just with words, but with those numerical values that give us some proof that'll back us up. All right, let's go back to these notes. And we'll continue on. So all of that work, just to reiterate this is what it takes to fill in the data to the equation that we had, that formula that we had a couple of slides ago, and find the linear correlation coefficient. So if you had to calculate it by hand, first of all, I wouldn't suggest doing it by hand. I would use a computer program, but your calculator does it for you. We know what the value means, and that's the most important part. All right, we're going to skip over our activity here. Okay, let's look at this data. Determine whether a linear relation exists between time to drill 5 feet and depth at which the drilling begins. Comment on the type of relationship. So we managed that part. There was a positive linear correlation. We can find a relationship there. So we know that. Let's look at this one. According to data obtained from the Statistical Abstract of the United States. So you got all this data to pull from. The correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.94. So that correlation coefficient is high. What we want to know is, are they related? So read that carefully and see what you think. Look at the information that we're looking at. The correlation between the percentage of female population with a bachelor's degree and the percentage of births to unmarried mothers. Now that high correlation coefficient, 0.94, says that the relationship on the graph of these two things is very strong and positive. But does this mean that the number of bachelor's degrees in females causes a higher percentage of births to unmarried mothers? Think about that and tell me what you think. Does one thing cause the other thing just because we've got that high correlation coefficient? Does one cause the other? Well, hopefully you're thinking the same thing I'm thinking. There's not a causation here. There's just a correlation because both of those have been increasing over time. One hasn't caused the other. I think we talked about flu shots in elderly before we left school when we were in class talking about chapter 1 stuff, and we were talking about how careful we have to be about assuming causation. And we said, well, it's not necessarily that the flu shots are preventing these older people from getting sick. It's a lot of other things are playing into this. So how social they are, what their health was beforehand, all of these pieces contributed to this. So there are lots of other things contributing here. It just so happens that there has been a common trend, but we can't say that one thing causes something else. So looking at the bottom of that slide, it's really important to note that when we observe something like this, we cannot claim that one thing causes something else. We can only claim that one thing is the cause of something else when we're designing an experiment. So in this case, we've just observed that this has happened. We haven't designed an experiment. And that's the only way we can describe causality. We've talked about lurking variables. And this is another place that it shows up. So there's something else going on there under the surface. It's kind of lurking. We didn't take it into account, but it's still there and related to both. So look at that example. Ice cream sales and crime rates have a very high correlation. So I can find data that matches up no matter what I'm looking at. It doesn't mean that local governments should shut down all of their ice cream shops so that they can shut down all of the crime. The lurking variable there could be the temperature. If it's pretty outside, we've got more people going to get ice cream and more people going to get in trouble. Okay, so we've got something else that's connecting those two things. Let's see. Let's skip that example. I think you can go back and look at that one. It's talking about how much soda you drink and the connection with your bone density. So you can go back and look through that one and look at some of those lurking variables that might explain that. So I wanted to get to this part before we finished up for today. Looking at least squares regression. So least squares regression is something that you have already done. We've already talked about it today. It's just the line of best fit. It's the fancy name for the line of best fit. So think about Algebra 1 again. We're going back to that a lot today, so hopefully you remember. I know it's been a while for some of you. But if we had these two sets of data, we've got x values and y values, we can find a linear equation to represent the relationship here. So in this example, they've just done a really simple Algebra 1 thing. They've picked 2 points from that set of points, found the slope and the y-intercept, and created one possible linear regression line for that. And that's what that line looks like. And we could use that line to make a prediction for something else. So this says use the equation to predict y if x is equal to 3. So we're good. We can plug the 3 in and we can find the y value that matches that. And based on that information, we can find a prediction. Now, when we find that prediction, it is just a prediction. It's going to be on that line somewhere because the line is what I'm using. The points are scattered. So looking at this one, the black dot is the prediction that we made. The blue dot above it was the actual measurement that we got when we went back to our data and had that value. 3 and 5.2 was the actual value from our data. 3 and 4.75 was what we got when we tried to make the prediction. Now, the difference between those values is called the residual. The residual is the actual value minus the predicted value. So that's really important. The residual is the actual, what we observed, what we measured when we went out and looked at whatever the information was, minus the prediction that fell on that line that we found. So actual minus predicted, or observed minus predicted, is your residual. So when we find the least squares regression line, it's actually not just the line that we get when we find the slope and the y-intercept, or not just what we get when we type it in the calculator. What happens is that we're trying to minimize the sum of the residuals. So or the squared residuals, actually. We're trying to minimize the sum of the squared residuals. And residuals can be referred to as errors. It's just the difference that we're looking at. And our predicted values are represented by that y hat. See the y with the little like caret sign above it? We call that y hat, and that's how we represent our predictions. So we're trying to minimize the sum of the squared residuals. And that's what happens when we press that AX plus B button in our calculator. It's minimizing those values. So we've always said y equals mx plus b. Now, of course, in statistics, we have to switch it up a little bit, and we want to have a brand new formula. Actually, it's not brand new, they just put different letters in it. But when we find that least squares regression line, it's going to be y hat instead of y. So that's going to be our prediction is equal to b1, same thing as the slope, x plus b naught, or b sub 0. Same thing as the y-intercept. So look at that and make those connections. Y equals mx plus b, same thing as y hat equals b1x plus b naught. So just like we can find the slope from information that we have, we can find the b1, the slope of our least squares regression line, from information that we have. R is still the correlation coefficient, and S is still for the standard deviation. So the ratio of the standard deviations, and we're still doing basically the difference of y over the difference of x, but it's the standard deviation of y over the standard deviation of x, times that correlation coefficient gives us our slope. And if we plug in the information that we know, we can find the y-intercept, or the b naught. So basically, we're taking the same information and switching it around. So these are just some explanations showing the difference between your x variable and your y variable. We know we're dealing with two variables in this case. So let's go back to, we will finish with this and I'll take any questions that you have. And this will cover chapter 4. The only thing left are a couple of, one more example and some summary things. Let's go back to the data that we had and find the least squares regression line. So we've already done that. I'm going to switch over and write this down so you can see it. So the equation for our least squares regression line is y equals point, let's keep it consistent, y hat equals 0.011553. I'll keep all of those. X plus 5.5273. We'll round it. So that's our least squares regression line. We found that earlier when we found our correlation coefficient, because the calculator gives us all of that at the same time. Now, the next thing asks us to predict the drilling time if we start at 130 feet. So we want to make a prediction if we plug 130 in here for X. So we can just type that in to our regular old calculator screen. And when I type that in, I end up with a prediction of 7.03. We'll round to the nearest hundredth. That's my prediction. If we go back and look at that table of information that we had, the actual Y value, let me go back and look, for 130 was 6.93. So we have an actual and a predicted value. Once we have an actual and a predicted, we can find the residual. Now remember, the residual is equal to the observed minus the predicted. So my predicted value was more than my actual value. We can find the residual here. This is the observed, and this is the predicted. So the residual is equal to 6.93 minus 7.03. And our residual is negative 0.1. So we were really close on that one. The point on the line and the point from our data were extremely close, and that's great. And the next thing, if we go back, that asked us to draw the least squares regression line on the scatter plot of the data, and we had already done that. We had our calculator graph both of those together, and that way we can see all of that at one time. The answers are on here, so I talked through them, but they're there. We can look back at that. The last thing, make sure, again, this is an algebra thing, but make sure that you know how to interpret slope and y-intercept and what those two things mean. We talk about that in Algebra 1, Algebra 2, pre-calculus. Anytime you're dealing with shapes of lines, slopes of lines, directions of lines, you talk about what those mean. But it's really important because a lot of times we get lost in just dealing with the numbers and we forget that we're applying these to actual real life things. So make sure you pay close attention to how to interpret both of those. The slope is always useful, the y-intercept, not always. It gives us a starting point, but sometimes it's not applicable. So make sure you're careful with that. Okay, so that covers all of chapter 4 that we needed to get to. We will talk about R squared next time, or I'll give you some information on that.